Hello, my name is Akemi and my tutorial is on density-based spatial clustering of application with noise. I have my table of contents where I'll be discussing the major points in my slides. Introduction to DBSCAN is one of the clustering techniques which can be used for clustering data points based on density. It works by distinguishing clusters as regions of high density separated by areas of low density, unlike K-means which assumes spherical cluster or convex cluster. To identify clusters of arbitrary shape, it does this by grouping together of areas with many samples. The deep ability to do this makes it very useful for performing clusters under noise conditions. This means that DBSCAN can dictate outlook, which makes it very versatile. And this is how K-means perform cluster and the perform clusters. K-means perform in a spherical or convex manner, while you can dictate arbitrary shape like this. So the key concept of the epsilon. This is a distance threshold defining the neighborhood around the data. 2 points are considered neighbors if the distance between them is less or equal to the epsilon. I'm going to use this diagram to explain this. Let's consider this point as point A and this point as point B and this as point C. Don't mind my handwriting. So each point A and B has a circle with radius called epsilon. So what this epsilon does is it defines how far it looks for neighbors in this circle. Alright, and point A is a cut point, and to be a cut point, a dot or a point must have at least a minimum point inside the circle. And we define my minimum point as 5 here, and that means a point must have at least a minimum point in a circle. This means that point A is a cut point because it has 1, 2, 3, 4, 5, 6, including itself 7 points, which is more than the minimum points that we define here. So this means that point A is a cut point. Then other point, consider this point B, which does not have enough points in its own circle. It cannot be considered as a cut point, but it is still inside. This point B is still inside the circle of the cut point. So that makes it a neighbor of the cut point. And the definition of a border point means a point that is not a cut point but falls within the neighborhood of a cut point. And noise point outlier is if it's not a cut point or a means it's a noise point or outliers. How does DBSCAN works? There's a short video here that demonstrates how DBSCAN works. It works while I explain how it works. So it starts by initialization. It starts with an arbitrary data point that has not been visited. Then moves to the neighborhood query. It finds all data points or points with a distance epsilon from the starting point or called neighbors. Then it checks for the cut points. If the starting point has mean points or more neighbors, it is a cut point. Remember the definition of cut points, and a new cluster is initiated. Otherwise, the point is labeled as noise. Later, this point might be included in a cluster if it is within the neighborhood of a cut point. Then expand cluster, it possibly add all density rich points within the distance of cut points to the cluster until no more points can be added. Then it moves to the next point. It traces this or repeat the process for the next unvisited point, leading to the discovery of cluster or noise. These points here are called tagged noise points. Let's read them as the noise points. Why this form a cluster and this form another cluster. So it says we have 2 clusters in this data set. Advantages of DBSCAN. Unlike K-means which assume a convex clusters or spherical shape of clusters, DBSCAN can find clusters of arbitrary shape or any shape at all. Then DBSCAN can identify outliers, which makes it robust in the presence of noise. Then you do not have to specify the number of clusters when you are working with DBSCAN algorithm. Then few of the disadvantages of DBSCAN is when you are selecting your hyperparameters, the epsilon and the minimum samples, it can be challenging and data dependent. And DBSCAN may struggle with datasets containing clusters of varying densities as well. So because DBSCAN needs to compute distances between all pairs of points, and there might be a case where you have a very large dataset, this can cause it to be computationally expensive. So how the algorithm works, I imported my to use, then I create the standard scalar object, then the result of the standardization is stored in the scale.df. Then I extend my scan objects from the libraries which I imported. I pass in the hyperparameters. I set the EPS as 0.1 and the mean samples as 9. Then I fit the DBSCAN model here. And I created a new column and called it cluster, and assigned the cluster labels as generated by the DBSCAN model. Then I use dot values to return a numpy array. Then I check the data frame again. Okay, the next thing is I want to know the number of data points in each clusters. So what I did is value.count. I set it returns this. It says in first cluster it has about 992 points. And notice that here is -1. In DBSCAN, where you have -1 is considered at the noise point or the outlier. So here did set the EPS to 0.1 and the mean samples to 9. Then the silhouette score, which I'm going to talk about in the next slide and what it means. And here is the visualization of the clustering technique. And we'll notice that we have a lot of noise points, and yeah, it has about 1, 2, 3, 4, 5, 6. It has about 6 clusters and the noise. One of the ways to optimize the algorithm is to use the best hyperparameters. So in this tutorial, what I did is I used silhouette score to find the best hyperparameter and to optimize my data. From the previous slide, I've imported my silhouette score as SS, and I pass in the scale.df and the number of clusters. Then it returns the accuracy of 0.2 as discussed in the previous slides. Initially, what we just did here is to guess. It's just using our intuition to pass the number of EPS and mean samples, and using this approach can be too difficult to know how well our algorithm fits. So it is best to optimize and to evaluate the accuracy, and to do that we use the silhouette score. And it might interest us to know that when using silhouette score, the best value is 1 and the worst value is -1. And when we have values near 0, it indicates overlapping clusters, and if they are mislabeled, we get negative values. So here, silhouette performance is 0.13, and there is a room for optimization. There is a way we can better the score. 0.213 is not good enough. Remember I said the silhouette score, the best value is 1. So it is best when our values are approaching 1, right? So what I did here is go back to the parameters, give it some new values, some new EPS, some new mean samples, 0.22 as mean EPS and 18 as mean sample. Then it returned a 0.63 silhouette score, which is doing way better than the previous one. And what I did next is do the value.count to know the number of points in each cluster and to know the number of clusters that we have. Then yeah, I have 4 clusters and the noise point here and the noise point. Then I visualize this result to see how it's going to look like. Using 0.22 and the mean sample as 18, the silhouette score returned 0.636, as you can see here. So this silhouette score is one of the quick way to evaluate the clustering performance, and we do this by exploring different combination of EPS and mean samples. We can write this line of code to help us return or identify the hyperparameters values that use the best clustering result as seen here. So with silhouette we can know how well our model is performing. So we move to the optimization techniques to choose the right EPS and mean samples. The EPS value defines the neighborhood size, and we must know that if EPS is too small, many points will be labeled as the noise points, and if it is too large, clusters may correctly merge. So other ways to optimize our DBSCAN is to use k distance plot, silhouette score optimization, which we did in this tutorial, Then we can use the grid search CV, then randash, then Bayesian optimization. And one of the best way to find the right mean samples is to use the good rule of thumb. We have the application of DBSCAN. DBSCAN is widely used in different areas. It is used in anomaly detection, in fraud detection, and in cybersecurity. It is used in image segmentation, where we use them in medical field for medical imaging and object detection. Then it is used for segmentation as well, in performing e-commerce and marketing. Then in geospatial analysis, example of that is the traffic clustering. DBSCAN is so good for density-based clustering and anomaly detection. And one of the advantages is that you do not need to specify the number of clusters you're going to use, unlike KMIN, where you specify the number of clusters. And DBSCAN is best for data with arbitrary shape. But one of the disadvantages is that it struggles with data sets that has varying densities. Then we use silhouette score to evaluate the performance. So these are the list of materials that has built my understanding on DBSCAN, and you can read more on DBSCAN. Thank you very much.